Hello everyone. Thank you, RP, for your introduction, and thank you everyone for being here. I'm Unsoo from MIT Media Lab, and I'm so excited to talk about our research on food and liquid sensing in practical environments using RFIDs. This is a joint work with my colleagues Junshan, Alaa, and Fadel. This work is motivated by a simple question, which is, can we sense food and liquids in closed containers even without opening them? So we've all experienced the situations where we pick up food items and started wondering, is it safe? Is it authentic? Has it expired? We might look at expiration label or date, but we can't know if it is a fake or not. So in fact, fake and contaminated food leads to thousands of cases of illness and death every year. So a low-cost solution would bring a great benefit to our society. As we thought more about this problem, we realized that many of today's products already have RFIDs on them. RFIDs are batteryless stickers like one in my hand, and they have been adopted by many industries in order as a replacement to barcodes. And today, hundreds of billions of items are already tagged with the RFIDs. So if we could use these same RFIDs for food sensing without modification at all, then we could bring a low-cost solution to lay consumers. And that's exactly what we did in this work. So let me explain about the basic principle. Our approach is to exploit the wireless interaction between an RFID on the container and the content of the container. So without being direct contact with the contents, the RFID will wirelessly interact with the content, and the interaction is governed by the dielectric constant, which is denoted by epsilon. So because of this interaction, when the RFID tries to communicate, this wireless signal is impacted by the content. And we designed an RFID reader that can extract the features and that can to be able to infer if the content is a fake or authentic. In this talk, I'll be telling you about our project RFIDs, the system that can measure properties of foods and liquids in containers without requiring direct contact. And it works accurately in practical indoor environments and generalizes to unseen content compositions. And we implemented and evaluated this system in practical indoor environments, and it shows more than 90% accuracy across different applications. This technology has a lot of applications. The first application is adulterated infant formula. Back in 2008, in China, more than 50,000 babies are hospitalized because of adulterated infant formula. It is a huge problem in China, and I will show you how RFIDs can solve the problem. And second application is a fake alcohol. Every year, hundreds of people die or go blind because of drinking fake alcohol. And also, I'll show you how RFIDs can address the problem. And the third application is fake drugs, which is an ongoing problem in many developing countries, especially in Africa. And there are other applications. So this is a counterfeit perfume, and this is a headline from last week. And also there is another one is a wine fraud, and so on. Now that I've told you about some of the examples of our applications, let me go back to our key concept. Remember that our key idea is that the RFID interacts with the content, and we can extract the features from the RFID and infer if the content is fake or authentic. Actually, a couple of years ago, we tried this idea and on fake alcohol experiments, and we published these early results in Hannes paper. let me tell you what I mean. Let me tell you about the experiment. We took one bottle with authentic alcohol and we put an RFID on it. Then we extracted a feature, frequency features like this, and we took another bottle with a fake alcohol, and we also extracted a feature like this. And we repeated the same experiment in the same few times in the same environment and trained the classifier, and we got more than 95% accuracy, which was very promising. We tried the same experiment in the different environments. So for example, we took authentic alcohol bottle and placed it in a supermarket style setup. As you can see here, there are lots of reflectors around it. So the new feature in red shows that it is much more like a fake alcohol than authentic alcohol. And this is why when we use the same classifier as before, the accuracy drops from 90% to 50%. So here, the problem is the RFID responses are not only impacted by the content, but also by changes in the environment. So it prevents us from generalizing to new environments. So we can think about a trivial solution to the problem, which is I can collect a whole lot of measurements. So for example, here, we can take a measurement from authentic alcohol, and we can move it around to different locations and get measurement from those locations. Then we have to repeat the same thing for fake alcohol. Also, we can move it. We would like to move the measurement set and repeat the same thing across different environments, like in supermarket, kitchen, living room, or cafe. Then we take them all and feed them to classifier. Then we might have a great accuracy. But the problem here is that it requires extremely expensive data collection process and does not generalize well to new environments or unseen contents. So ideally, we'd like to synthetically generate measurements from unseen environments. So we want to take an authentic alcohol, for example. Then there is an operator that allows us to apply different environments. Then we can get a large number of synthetic results. And we can use these results for training the classifier. To do so, let me give you a simple background on how to decompose the RFID channel. There are mainly two different factors that impact RFID channel. The first effect arises from the interaction between RFID and the content. And we call it coupling effect and denoted it by C as a function of epsilon. And second effect arises from the propagation and the multipath. And we call it multipath effect and denoted by M. The overall response H is a product of C by M. So here, to apply different environments, we need to generate different M, which means multipath effect. But the problem is, how can you isolate multipath effect to generate different environments, knowing that our measurement is always impacted by both effects? So to solve the problem, we introduce multipath kernel function which allows us to generate environment-only features. Let me tell you what I mean by that. We take, let's go back to our basic experiment. We take a measurement from authentic alcohol in two different environments, and we extracted the features like this. Let's call them H1 in red for top setup, and and the H line of sight in white for bottom setup. And the multipath kernel function simply divides them to generate environment-only feature. To see why this is true, let's substitute H by coupling and multipath effects. As you can see here, both measurements have the same content, so this leads to both measurements have the same coupling effect. So we can easily cancel out the C component. So it is M1 divided by M line of sight, which is the output of multipath kernel function, and independent of content and dependent on environments. So now we can isolate M feature. So we are gonna take measured real-world environments to generate unseen synthetic environments. The problem of taking real-world measurements to generate the synthetic data usually can be solved by generative model from machine learning. We've seen lots of models like this, in systems, for example, like deepfakes, which can produce video or face of the humans that who do not exist in real life. And the specific types of generative models that we use is variational autoencoders, or VAE. I will not go into details how it works, but this VAE has a nice properties. For example, like it can reflect the sparsity of the environments and the Gaussian nature of wireless channels. So it is good for our problem domain. So to summarize, we can get the measured real world, taking the measured real world environments to generate unseen synthetic environments. But the problem here is that we cannot use these features directly for training the classifier because there are no content feature here. There's no fake or there's no authentic feature. So these are just the environments. So what we are going to do is re-embed the content feature. All we have to do is just take a single measurement and multiply by it. Then we can get synthetic measurements from unseen environments. By doing this, we can apply different environments. We can do the same thing for fake alcohol, and then this new synthetic data allows us to train the classifier to accurately classify contents, even if it's in unseen environments. So here, the key message is multipath kernel and the VAE allow generalizing to new and unseen environments, which is great. So, but are we done? Actually, there is one more big question, which is, how can it generalize to fake content which we have not trained on? So far, we have assumed that we know what the authentic and the fake one is. But in many cases, most of the time, we don't know what the fake one is. So if we were to feed different fake one to a classifier, that it might not perform well at all. So to solve the issue, we leverage the same multipath kernel function to detect anomalies. So let's remember that the multipath kernel function just divides measurements in multipath environments by measurements in line of sight environments. So, but here, if we take the measurement from fake alcohol, then the response will be different. And here, the coupling, and because the two materials are different, we have a different epsilon, which means the C component cannot be canceled out. So the output feature is dependent of content, and we can use this dependence actually. So in high level, by using reconstruction loss of trained VAE as an anomaly score, we can separate between anomaly and authentic one. So also we can use RFIDs combines. RFIDs can combines anomaly detection with transfer learning to generalize to new and unseen content. So this is a prototype implementation. We used this is a RFID antenna, and which is connected to USRPs N210 and X310. And we used the off-the-shelf RFIDs without any modification. So with EPC Gen 2 protocol, and we adopted 2 frequency excitation from Mobicom 17 paper. And for 500 to 1000 megahertz frequency, we extracted amplitude and phase as a feature points. And we collected more than 2,000 samples from 20 different environments for testing. We tested a variety of applications, for example, alcohol, baby formula, medicine, perfume, and wine, which I talked about it in the beginning of the talk. And we also tested with fake oil and soda brands. The way we made this are well described in our paper. And this is the classification accuracy when we train and test in different environments. X-axis are different applications, and Y-axis is classification accuracy. So first, let me show you the baseline, which is our previous model accuracy. As you can see, most of the accuracy is around 50 to 80%. This is because the RF model, this model, even only work well in the same training and testing environments. But here, we tested in different environments, so the accuracy is really low. Then this is RFIDs accuracy. As you can see, it has much higher accuracy. It's usually more than 90% or around 90%. And some of you and the wireless people in the audience might be wondering, like, why don't we just use a ray tracing model with VAE? So we actually tried it, and as you can see here, it performs actually even worse than Hannet's paper model. So this paper, there's one more interesting question here. Why do we have this accuracy difference for different application? Remember that our RFIDs is impacted by the dielectric difference. So we measured actual dielectric difference by using this probe kit. So here is the accuracy versus dielectric graph. The x-axis is a dielectric difference between authentic one and fake one for each application, and y-axis is a classification accuracy. And remember that the fake medicine had the highest accuracy, and it shows the largest dielectric difference. And fake oil shows the lowest accuracy and the smallest dielectric difference. And if we plot all of them, we can easily see that there is a log linear line that represents we can see easily the relationship between classification accuracy and dielectric difference. It verifies that the RFIDs can be impacted by dielectric difference. To conclude, we built as RFIDs, and it is able to transform inexpensive RFIDs into non-contact liquids and food safety sensors. And to do that, we introduced Multipath kernel and employs variational inference to generalize to unseen environments and contents. And for future work, we want to generalize it to new applications and other environmental factors such as container material. With this, I'll wrap up my talk, and I'm happy to take any questions.
Hi, is from UC San Diego. So my question is, you have shown the content feature which is dielectric, which works very good for liquid that you have shown. Mm-hmm. What about like other food material which are not liquid? And do you have any other features other than dielectric which will work on these kind of items?
Thank you for your good question. We tried the meat, which is kind of solid, but the accuracy is not that high as much as our liquid case, because I think the sample is not homogeneous for solid case. So yeah.
Okay. Thank you.
Sparran Kumar, Carnegie Mellon, great talk. You kind of read my mind when you showed that result on ray tracing, because I was about to ask you, why didn't you use ray tracing? But can you give us some intuition on why it performs so badly and why we need to use machine learning to understand multipath?
I think ray tracing cannot capture the realistic environments. For example, like there are diffraction and scattering effects, but our conventional ray tracing model cannot capture that kind of real environmental effect. That's
Did you consider other models or only ray tracing?
construct what?
Did you consider other models or only ray tracing?
I just follow the one in textbook.
Hi, Danny Chen from Princeton. Have you tried to measure your work on a different metric, just purely measure it as measure dielectric factor? Like you don't use it as a classifier, but just say, I use my tool to measure the dielectric factor directly. What would be the accuracy?
Sorry, can you repeat?
So basically, you essentially can use RFID to measure the dielectric factor of the material. Have you tried to evaluate your work that way to see how accurate can it be?
Sorry, I cannot understand your.
So you measure epsilon.
I think let's take that offline. We are running
Okay.
out of time. You have an announcement?
Actually, one more round of applause. Thanks.
All right, thank you.
I just wanted to make a really quick announcement. We wanted to apologize for some of the noise you were hearing. There was a fire safety thing that is happening, and so unfortunately the fire marshal gets to run a generator, and so that was what that noise was. So I believe it is probably done for the rest of the talk, so our apologies to the speaker.
So our next talk. Oh, you have a question?
So like milk versus spoiled milk, right? So in that case, like dielectric difference wouldn't probably change a lot because it's the same fluid. So like how would your classification accuracy compare for that application?
You mean your question is how can we detect the, for example, like spoiled milk for as a time? I mean,
Yeah, yeah. So
actually, our previous version have a milk spoil detecting milk spoiling application, and we use the regression model for like in time versus dielectric change.
okay, thank you.
Is it all right?
Again, thank the speaker.